Okay, so now everything is hooked up, and let's turn on the variac and let's look at a meter. This is hooked up to the B plus, and as you can see, the B plus is climbing up to 620 volts, and then it drops down. And when we look at here, we are at the 1 ampere scale, like 0.8 amp power consumption. So now let's so we have the output connected to our oscilloscope, and what is the output here? So these are the speaker binding posts, and then we have a 15.6 ohm power resistor hooked up there, plus the scope probe is hooked there too. And for the input, through an RCA cable, I have our signal generator hooked up. Let's turn it on. Okay, so now we are feeding a 2 kilohertz signal to the amp, but I have the volume control at 0, so it doesn't show anything on the scope. So let's give some juice. Okay, so now the scale is 5 volts per division. So let's just, so eventually we get 2.2 divisions. So that's about 11-12 volts on the outputs. That's around 6 watts of output at the moment. And what are we using? So this is sine wave, and it doesn't look like a nice sine wave at all. Let's see. It's kind of finicky. Okay, but as you can see, it's not a perfect sine wave. It's like halfway between a triangle wave and a sine wave. And when I did not have the zeners on the screen, and there was only 2.7K connected between screen and plate, then the waveform was much nicer and much more symmetrical. Let's shift to triangle waves. Even the signal generator. And that's not bad, that's pretty good. And now let's shift to square wave. Okay, let's just find it here. And you see there's some ringing there at the bottom. And if we decrease the size, let's go higher on the scale. So you see there's no ringing there. The ringing has disappeared. Now we are at the 1 volt per div scale, so that's 1, 2, 3, 4, 5, 6. So we are about 6 volts at the output. And here we do not see any ringing. And when we go higher, now we start to see some little bit of distorting there, but it's not ringing yet. And now you see the ringing here. So this is at 1, 2, 3, 4, 8 volts output, and we can already see ringing. So without the zeners, this thing started to happen at this frequency only when after 20 volts output. So that's like we drastically decrease the output power of the amplifier by adding 120 volt zeners there. And when we see the 20 volt output here feeding those 16 ohm resistors, that means 25 watts of clean output power at 1 or 2 kilohertz. Okay, so you see, now we went lower and it's nice and clean, and now it gets really nasty. And you see, when we go very high power, then you can see that sharp overshoots there. So this is how. So there was a measurement by John Atwood, who measured these output transformers. Actually, he made a list. I think it was sometimes maybe in the 80s or 60s, like a really old measurements of all the output transformers of all the famous audio gear that was available. And he published that this output transformer can handle 25 watts output, and he said that he has seen a lot nasty ringing, and this is that nasty ringing that he has seen. So you see at here, that's the ringing part, and that shows that we are starting to have some distortion due to either the transformer or the tube or both. And when we go to even higher power, now we see rising those overshoots. So when you start to see that, that's when it starts to become really nasty. So now this will show up as a really bright and harsh sound. So let's dial that more down, and let's go much lower in frequency. So now we went down to 22 Hertz. That's, I think maybe let's go a little bit higher in frequency because it will be really hard to see. So now we went up to 98, 99 Hertz. Okay, and as you can see, it's still pretty hard to see that. But it's not nice. It's slanting a lot. So we do not see nice steps, but the steps, when the step occurs, there's a jump and it slopes down. So it means that there's a dynamic compression going on. So there's it means that the power supply cannot handle, cannot sustain that signal, or there's something going on within the tube, some sort of negative feedback that just decreases the signal. So in our case, it's that negative feedback going on in the tube because of the zener that we placed in, because without the zener, we do not have this extreme slant. Even at 20 Hertz, there's a tiny bit of drooping you can see, but nothing like this extreme drooping. And if we increase the output, then the drooping becomes more and more extreme. You see now it's like really pronounced and really nasty. Yep, so this is what I wanted to show, that it's not a good idea to put in zener diodes to protect the 807s, because as I said, I've been running 807s in triode mode with 500 volts on the plate, connected with a pair of not with a pair, just through a 2k ohm resistor, and it's happy and safe. And if you put a zener there, then you drastically drop down the available power output of your amplifier, and your bass response will be really skewed. And if you look at the sine wave doesn't look that bad. And you see that's why when they show measurements, they often use sine waves, because you cannot see the true nastiness through sine waves. It just looks much more perfect, much nicer. And when you look at the square wave, you see already that break up there, the slight ringing. And of course, this is also something really extreme, because this never ever happens in music. So there's no music content that uses square waves, and there's also no music. Well, sine wave is a little bit much more closer than real music, but real music is way more complex. So it's like sine waves upon sine waves upon sine waves. So it's much more complicated than this. Maybe we can do a video on that too. So right now I will show you what happens when I power down. So first let's just turn off our signal generator, and now let's turn off our variac, and you see the power consumption drops, and let's see the high voltage. It drops really fast because the tubes are still conducting and they are draining the capacitor bank. And now as the filaments cool down, the tubes do not conduct anymore, so they will not they will not deplete the capacitor bank fully. So the drop will just start to slow down, and there's a small voltage remaining. So right now we are measuring, you see that's where the leads are hooked up. So we are measuring the C2 of the input filter bank. And from the C2 we are feeding here, or C3, and the C3 feeds C4. And between these two I have this trick that I learned from Stu, to put in a diode, not just a resistor. And the diode, what it does, it blocks this capacitor for feeding back signal to the preceding stage. Because what happens is that when the capacitors charge, the first should feed the current, so it should fill up the second cap, the second should fill up the third, should fill up the fourth. But what happens when there is a big signal and your phase splitter draws more current, so this capacitor drops in voltage compared to the first. In that case, this capacitor will not be supplying that, but will be drawing current and voltage from the first cap. And that thing is not the very best thing that can happen, because your first capacitor, that's your input, that feeds your input tube, and is the most sensitive to any changes. So you want to protect it from the parasitic feeding by that capacitor. So this capacitor is supposed to supply that cap and not draw power from that. And when you put in a diode there, that allows filling of this capacitor, but it does not allow the other scenario. So then your cap that feeds your input tube will be always protected from the parasitic or motor boating effect of the preceding stages. And that will simulate as if the same effect as if you had a separate power supply for that stage. So if you want to vastly upgrade your power supply, you do not need a separate power supply for each tube stage. Just put in diodes between each stages, and that will give you about 70-80% of the effect, as if having completely different power supplies for each of them. So we are here right now. You see it stopped around 22 volts on C1, and you might think that okay, now it's safe to work on the amplifier because it's only charged to 22 volts. And yes, 22 is still 22, but if that zaps you are still okay. However, that's the charge on that capacitor. Here we don't know what the charge is, so let's take a measure there. So we have a second meter hooked up to the ground, and let's measure here C2, and that also this meter measures 22 volts, so it's the same. But let's look at our first cap that measures 53 volts. And you see that's because these two are protected from each other. So this is not, so if there is a drain here, then that will not drain this capacitor as much as it drains the rest. So you see here it's at the same voltage as that capacitor. So we are measuring the same voltages on all three of these guys. And this one, as it measures 53 volts, that can give you a really nasty shock. So that's why you want to use your bleeder resistor. This is what is this? 10k 20 watt resistor, and you hook up. Okay, this is a little tricky. So hook up one to the ground, and you hook another one up. You see I have some insulation there to help. Hook one up to here to the positive lead, and let's measure what's our voltage now. And you see it starts to drop drastically. It's 1.2 volts. It's bleeding the voltage down, and also the voltage and then the preceding caps, it's dropping as well as the other one shows. So you see now it's down to 1 volt, 0.2 volts. So now the amp is safe to work on. So after powering it off, now you can work on the amplifier again. But I do recommend also, just to as a safety precaution, just to turn off your amp, and you can also unplug its power cord, because you don't want any surprises, like for example accidentally flipping on the power on your Variac, or if you have kids or pets and they flick it on while you're working on it and you get yourself electrocuted. So that's a nice tip for everyone, a nice safety precaution. And what else? Oh, by the way, this video is for demonstration purposes only. If you are not qualified to work on electronic devices, then do not attempt to do so. This device harbors over 600 volt at startup that can easily kill a healthy adult male, and will with 100% electrocute small animals and children. So you have to be absolutely sure what you are doing. You have to be qualified to working here, and children must not come close to such devices, and you have to be really careful if you work on this amp, if there are children around you, to make sure that they are not coming within 20-foot radius of you. Animals, they are very interesting. Cats can intuitively feel electric charge. They will not come close to the amp when it's on and when you are working on it. And one more trick is that when you are done with your work, before you flip it on, please do not forget to remove your bleeder resistor, because if you turn it on and the bleeder is still on, then it will start to glow yellowish, first reddish, yellowish, and then you will hear a large boom, and probably if it's like touching your bench here, your bench will catch on fire too, so you can burn your house down. Anyways, just be safe, use safety first, and I hope this was helpful for everyone.